So day 3, and once again, a completely different post-processing code. Before I get started, I know that a number of you are Python ninjas and are well advanced in terms of programming techniques and whatnot. But for those of you that are getting started or interested in learning more about Python, I just wanted to give an advertisement for this recent book on SciPy and NumPy, which was actually written by an astronomer, Eli Bressert, and that came out within the last year. And so if you're kind of at a basic level and like to learn more, I would encourage you to at least check out this book. I also have to say that, like Tom, Eli is also a pretty cool person and a good person to know. So if you run into him at a conference, you should definitely introduce yourself and find out what he's working on. One recent thing he's doing is actually working on instantaneous volume rendering. So instead of fiddling around with YT and doing the transfer function and then running it, he's setting up a program to do it within a web browser almost instantaneously. So it's pretty cool. All right, so on to what I'm actually going to be talking about today. So today I'm going to be talking about performing synthetic interferometric observations with the package CASA. And CASA is really a program that was written by observers for observers. So it's not really necessarily very friendly to theorists, but nonetheless you can actually use it to do some really interesting things and make predictions for some of these new interferometric instruments that are coming online. So an example of what you can do, which I'm going to be talking about tomorrow, is to make synthetic ALMA observations. So basically, I've saved all of my science stuff to talk about tomorrow. So after these 3 days of talking about these different codes and how to use them, tomorrow I will give you much more scientific justification and to talk a little bit more about my work. Okay, so here's my outline for today. Why do you want to model these type of observations? I'll try and convince you that it's a useful and important thing to do. Secondly, in case you don't have a background in interferometry, which I personally don't, I will actually go over some basics for what you might need to know as a theorist or think about. Then I will introduce you guys to CASA, this package for doing this data analysis and modeling, and finally a suggested project. Okay, so why model interferometry? So really, over the last decade, there's been an observational revolution going from single dish, single antenna instruments to multi-antenna and multi-dish instruments. And the foremost of those, and the most recent, is ALMA, which has been coming online over the past few years with an increasing number of antennas, and is still ramping up. And we're in cycle 1 now in terms of the observing. So other instruments are, for example, CARMA, and VLA, and VLT. So all of these are really a new kind of observations that are worth trying to understand and make predictions for, particularly in the case of ALMA, where we're really getting unprecedented resolution and unprecedented opportunities. So it's really a good time to make predictions and to get in the business of trying to understand the data in detail. So one more motivation is really in the old school astronomy, we had things like this. But now with these interferometric telescopes, we're getting these really exciting, very high resolution images of different things. So now we have a huge amount of data, and it's not just about blobology. Now we have lines, now we have a lot of different continuum, and we can combine all this data to really get a complete and detailed picture. So I'm going to take a brief aside to talk about some recent results of ALMA. And at the end of these, you might wonder, the data is so good, why do you even need to go about and do this extra step of modeling it? Because it's practically the real thing. But nonetheless, I think it's worth keeping in mind that there are limitations to what ALMA can do and regimes that you and your simulations can help to probe and explain. So one really recent observation is an evolved red giant star. Here's a movie basically zooming through the data cube. So we're going through in velocity space. And as you go through, what you see is that there are these rings coming out of the star. And this is resolved in very high detail. So not just rings, but you can actually see spiral structure here in the middle. So this is really incredible. Now, some of these shells are expected because basically at this phase of evolution, there are thermal pulses that actually throw up quite a lot of mass. So you get these shells of mass loss around the star. But then this interesting spiral structure, they think was caused by some kind of unseen companion which is orbiting the star and creating some of this spiral structure here in the gas. So it's really great observations. So another recent issue closer to star formation is the observation of very high resolution protoplanetary disks. And so before, the disk might be a single beam if you're lucky, but now with ALMA we have sub-arc second resolution. So here we have protoplanetary disk HD 14257, and then what we have, initially I think they had known that there was a gap here. Now they're actually able to resolve it. So it goes from apparently maybe 10 AU to 140 AU, and they think that there again might be some companion, some planet that's orbiting in here and clearing out the gas. But then a lot of this detail is trying to understand the evolution and structure of this disk here. So here we have it in continuum. We have it in, I think this is 13 or CO 3 to 2. And we have 2 micron, and then we have HCO plus. So you can see there's a huge wealth of structure. And the most interesting feature here is the asymmetry. So here you see this kind of finger pointing inwards. You can kind of see it again here. And they inferred from this that this is gas from the outer disk, which is actually being funneled in and accreting onto the star. So perhaps you've seen some of the cartoon artistic pictures of this, but it's really quite striking. And understanding this more in detail, in particular using high-resolution numerical simulations to try and predict and understand this would be a really great thing to do. Okay, so why else? Well, ALMA, aside from being very high resolution, has a very wide frequency range. So within these bands, there are a huge amount of different chemical species that you might be able to probe or model. So here is an online program that tells you about the different species in different bands. So here's band 3, which goes from 84 to 116 gigahertz. And you can see we have found 24,796 lines all in that band. So now there's almost a wealth of data, and trying to understand the chemical distributions and their abundances is also an important component. So in this case, you can see that there's a really rich problem here, because you can go ahead and you do your numerical simulation, but then you need to go back to Paul Clark's lectures, try and understand some of the chemistry, and then you need to model the lines, for example, using RAD-MC, and then model the interferometry of ALMA. So this is a huge wealth of parameter space, which you can explore using the techniques we've been talking about all week. So here's an example spectrum taken of a dense cloud core, and you can see all these lines that were just mentioned on the previous slide. So really there's a wealth of data. Now, the chemistry is quite difficult, and I think a lot of it is really not well understood. There are features that are not identified. People don't understand the abundances, how they change with time. So this is something where combining numerical simulations and chemistry and radiative transfer, you can be a huge help to making predictions and understanding what this wealth of data means. And of course, if you really want to do this, you need some molecular line transfer code like I talked about on Monday. Okay, so now interferometry for theorists. Okay. So interferometry for theorists. The caveat is that I am not a real observer. I don't do interferometric observations for a living. And so help with this lecture was provided by Scott Schnee, Todd Hunter, and Dave Wilner. So I'm indebted to them for a lot of help with some of these slides. So just as a show of hands, how many of you have actually worked with some kind of interferometric data or taken such data? All right. So we have some people that know what they're talking about. That's good. All right. So feel free to chip in if you want to correct or modify something I say. Yeah, but for most of you, this is probably new stuff, which maybe you haven't thought about too much before. So interferometry, in a nutshell, is that basically the sum of images from many little antennas is almost, but not quite equal to an image from one giant antenna. Okay? So the interesting part is the almost but not quite equal. Okay? So understanding what you actually can infer, what your pluses and minuses are in terms of using this observational technique. Okay, so the old picture in observing was to use a single antenna. So in that case, your resolution was simple. So your beam size was related to how big you can make the antenna. So the larger the antenna, the smaller the beam. So I think one of the largest telescopes or largest planned single dish telescopes is the LMT, which will eventually be 50 meters. But it's really hard and actually technically limiting to build such large dishes. I mean, you can imagine this huge frame, and it's difficult to point it, and then you have errors because the weight of the telescope needs to be very uniform and very well distributed and supported. So it's very technically a hard problem. So it's much easier to build a lot of smaller antennas. So in that case, the resolution of two antennas that are separated by some distance d is now comparable to a single antenna whose overall diameter is a distance d. So in this case, now you also have an angular resolution which you need to worry about, which is approximately lambda over d. So your resolution with these multi-antenna structures depends upon the distribution of separations you can achieve, the distribution of baselines. So on the small end, the telescopes have some physical size. So you can only put them so close to one another, which means that if you want to resolve larger structure, it can become difficult. Okay? And likewise, you have limits on the large end because you can only put them so far apart. Okay? The site has a finite distance, which means that you have some inherent range of scales that you can actually resolve. You can't get infinitely good resolution either in small scales or large scales. Okay. So some basic definitions. Physically, I think of two antennas and the signal from them as a two-slit physics experiment, right? So remember back to your basic physics and your basic diffraction and interference experiments. If you have some source here and it's shining on two slits, then depending upon the path lengths going through these two slits, the signal will either add up and get a positive peak, or it will actually cancel out and get a negative peak. So you basically get an interference pattern. And so this is what is actually happening when you have these two antennas. The signals that are reaching them have a different path length, and so when you add them together, you get this interference pattern. So between these two, you can actually construct what is known as a visibility. So it's basically just an interference pattern, where some amplitude tells you how much of a certain frequency component, and then the phase tells you something about where that component is located. Okay, so there are two key things that you want to know. So the most fundamental thing you want to know is the true brightness, the true signal in the sky. Okay? But what you actually get, what you get from combining these signals from the different antennas is not the true brightness, it is the complex visibility. So it's this interference pattern. Now, there's a classic theorem called the Van Zernike theorem, which basically says that these two quantities, the brightness and the complex visibilities, are Fourier transforms of one another. So I looked up the exact definition on Wikipedia, and Wikipedia says that this theorem says the Fourier transform of the mutual coherence function of a distant incoherent source will equal its complex visibility. So thanks, Wikipedia. If one of you guys who knows more about this could go and edit that page and make it slightly more transparent, that might be useful. But basically what it's saying is that by measuring the degree of coherence from different points, that is the signal at these different antennas, known as the visibility function, observers can then reconstruct the source brightness, okay, just by taking the Fourier transform. Okay? So converting between the real image plane and this complex visibility UV plane, which is this interference. Okay. So now we have the audience participation part of this talk. So if you can remember back to when you took your basic mathematical methods class, you probably did a lot of Fourier transform stuff. And it helps to understand the data and the recoverability if you know what the different Fourier transform pairs are. So suppose you're observing a point source, and the point source is essentially a delta function. If you take the Fourier transform of that, you get a different function. Okay, so we're going to do some Fourier pairs. Okay, so does anyone remember what the Fourier transform of a delta function is?
A uniform constant.
A constant, right. All right, good job. All right, so next, suppose we don't have a point source. Suppose we have a kind of distributed source or a diffuse source, which is a Gaussian. Does anybody remember what the Fourier transform of a Gaussian is?
Another Gaussian.
Another Gaussian. All right, great, this is easy. All right, next we have an elliptical Gaussian. How about that? Another elliptical Gaussian. All right, that's good. Okay, one more. What is the Fourier transform of a disk?
A sinc function.
A sinc function.
Sin x over x.
Yeah, so it's a Bessel function, one of the family of Bessel functions, which is the solution to those differential equations, yes. Okay, so a disk is slightly more complicated. And what you can notice is that there are now, because of this Bessel function, a lot of very high frequencies. So you have a much more distorted signal, which you can imagine could cause a lot of problems in terms of signals. Okay. All right, so now what if you don't have two antennas? What if you have a whole collection of antennas? So now what you have to do is something called aperture synthesis, which is where you basically combine the signals from all your antennas to produce a single image. And the idea is this image will then have the same angular resolution as one antenna the size of the whole set. Okay? So if we have a distribution of antennas, and they're arranged like this, so this is kind of like x and y. This is their distribution with respect to one another. Then over here, we have the visibility function that you get. So there's kind of an art to getting good visibility. The better that you can sample the visibility function, the more points you can put on this side, the better you will be able to resolve your image. The better the Fourier transform is going to be. Okay? So a couple of tricks you can do is use as many antennas as possible, which is partly why ALMA is such a big deal. There's going to be a huge number of antennas. Now, to sample a range of spatial scales, you also need a large number of baselines. Okay, so you don't want to put all the antennas the same distance apart. Next, you want as many samples as you can. And you can increase the sampling by taking advantage of the fact that the Earth is rotating, so the distance to the source is changing. So then this means that as the Earth rotates, each of these antennas traces out an arc in the visibility function space. Okay? And then you have a number of pointings along that arc. So you can also increase your sampling to get even better spatial coverage in the UV plane. Okay. All right. So now if you have a bunch of antennas, you might wonder, what happens to the concept of a beam? When you have a single antenna, your beam is probably basically a Gaussian. So it's nice and simple. It's probably pretty clean. But that is not actually the case when you have multiple antennas. So now we have a concept where we have a very complicated beam or very complicated point spread function. And in fact, they often refer to it as a dirty beam because in fact it is actually quite messy. So we're going to see how that looks for different configurations. Okay, so suppose we have 2 antennas. Then we have only 2 points in the UV plane. Okay, so we take one pointing and get a signal from each of the 2 antennas. So we get 2 points because there's a baseline from antenna A to B and a baseline from antenna B to A. Okay, 2 points. So then what you basically have is the beam is this interference pattern that you get from adding up the signals, and it looks like this. So that is basically as far from a Gaussian as you can get. It's a pure interference pattern. Okay. So now, what happens when you add 3 antennas? Well, 3 antennas, things actually get messier. You have now 6 points, but it doesn't obviously look like a good improvement. So we'll keep adding antennas and see what happens. All right, so now we have 4 antennas, 5 antennas, 6 antennas, 7 antennas. And what you can see is that now we're finally getting this kind of overdensity here in the interference pattern. So we're kind of converging towards a standard Gaussian beam. So there's still a huge amount of mess out here, which is referred to technically as side lobes. There's a huge mess here that's creating problems, but we are converging on a single beam. All right, so continuing, we have 8 antennas. 8 antennas times 6 samples. So if we take several different pointings from each antenna, 30 samples times 8, 60 samples times 8, 120 times 8, 240 times 8, and 480 times 8. Okay, so now you can see we've filled out, we really sampled the UV plane quite well. We now have this complex sampling. And in turn, this means that we have a much better, much cleaner beam. Okay? And it's approaching a Gaussian. And at this point, you could almost represent it as a Gaussian with some full width half max. So if you get enough sampling and enough coverage, then you are slowly converging to a single large dish observation. But, I mean, there's still these artifacts there. And artifacts will still cause problems when you're trying to do this Fourier transform and get information about the actual sky brightness. So to take care of this, what the observers do is then they deconvolve their image, or they clean it, to get rid of these beam side lobes. So here's a dirty image, which is their signal, which is convolved with the beam. And then the extra step is to deconvolve it and try to recover the initial signal. Okay? So it's not enough to just take the Fourier transform. You have to do an extra step of removing this messy side lobes. All right. So now we can take a look at what the effects of different UV coverage has on different images. So here we have an input image on the left. We have an early science configuration with ALMA, which is, I think, 16 antennas. And this is an observation for 10 minutes and 4 hours. And over here is full science for 10 minutes and 1 hour. So here, as you go from left to right, we have a signal that has a brightness of 5 sigma. And you can see as you go left to right, I mean, maybe it gets a little bit clearer. Here it's kind of a mess, it's asymmetric, but as you go to the right, it cleans up a bit. Here we have 5 different point sources with different detections, and as you go left to right, you can see the signal gets better. Mainly, it's the low detection signal that has the problem. So here, with this 10-minute observation, it's virtually absent. Here, it also looks pretty crappy, but as you go over here, you're recovering the scale and structure better. Finally, we have a synthetic Albert Einstein, and you can see Albert Einstein looks pretty horrible in the early science configurations, whether you observe him for 10 minutes or 4 hours. And then Albert Einstein starts looking a little bit better as you go towards 1 hour with full science. Now, to be honest, he still looks kind of crappy, but at least you can sort of recover that it does, in fact, look like Albert Einstein. Yes?
The Albert Einstein example, just missing long baseline. Is that right?
Yeah, so you can see there's these artifacts here that are coming in because of the incompleteness. And yeah, I mean, you do recover a lot of the large-scale structure. It still looks to me like some of the small-scale stuff is missing too. As here we have this blob here, and I don't see it over here. So it's kind of a mix of scales that are missing.
Particularly the early science.
Mm-hmm. Yeah, the early science is a mess. Definitely a large scale seems to be missing there. Yeah. Okay, so something to keep in mind that there is a kind of art form here that there is a loss of fidelity from one end to the other, and this is somewhere where numerical simulations can step in and then try and quantify the missing information, try and help put it back, try and interpret it. Okay, and something like this can be quite expensive to do these very high resolution observations, and ALMA is currently subscribed more than 10 to 1. So that means the probability of getting time is quite low. There's not that much of it, and people can't afford to have very large requests. So still, there's a lot of work that can be done and a lot of area for predictions to be made, which can then be followed up with ALMA if you can do it correctly. Okay. So there's one further issue with the observations, which is water vapor. So for a single telescope, you basically need to have good weather through the atmosphere. But the problem actually gets more complicated when you have multiple telescopes, because if there's anything in the atmosphere, such as water vapor, it creates different path lengths along the line of sight by the different antennas. And these path lengths can then vary as a function of time. So this creates noise and problems with your signal. So this is something that needs to be corrected for, or at least understood, and it imposes some underlying limits on how well things can be resolved. So in particular, in the models that I'll talk about later, you'll be able to put in some kind of underlying model for the water vapor. But this is also the reason why these interferometers are put at very dry locations, okay? So the less water that's there, the better it is for the interferometry. And so the point of this is that even if you have very good weather, you can still have this atmospheric variability that can create problems and lead to instability when you're trying to recover and combine the signals from these different dishes. All right, any questions so far? All right. So now I'm going to talk about CASA and how you might want to use this in your work. So CASA is different than these other codes. It's developed by NRAO, so it's not something that you will download and then modify yourself. It really is a software package where you can feed in your numerical simulations and then treat them as real observations. So I think there's little possibility for code development here. It really is a standalone package. So this is a Python-based package, and it's basically made, as I said, by observers for observers. There's a very large CASA guide on how to use it. And personally, I think most of the difficulties in using it are not related to the complexity of the software or related to the complexity of the program itself so much as the complexity of interferometry. So if you understand interferometry, I think this is a really easy package to use. You understand how to set the variables and what things to consider. But if not, then it becomes much more complicated. So there is a specific part of the documentation that's on making simulated observations. Okay? So you can check that out here, and hopefully that simplifies some of the other stuff about cleaning data and post-processing and analyzing data that you don't actually need to worry about. So to start off, I'm going to give you an example of something that I worked on with a student in terms of using the software package. Now this work was done by Gilberto Lopez at Harvard, and it was one of his, I think it was his junior thesis in astronomy actually. So this is in collaboration with Claudia Signowski, Chris Beaumont, and Alyssa Goodman. So the idea was to create a kind of pipeline to reproduce these ALMA observations. So in the pipeline, he starts with a simulated emission data cube. And then this 3D data cube is basically kind of like your raw emission data. This is fed through CASA and then observed with a specific ALMA configuration. And then once we have that as an output, we can analyze it just like observers analyze their data. And I'll tell you about the statistical tools briefly. And then make a direct comparison with observations. And further, you can go ahead and predict how well observers can recover fundamental properties given this whole pipeline where you're losing information each step of the way. So here, you lose information because you're going from 3D density data to 3D position, velocity. So you've lost position along line of sight, and you've lost 2 degrees of velocity in other directions. Then you have the emission, and then finally you have this issues with the resolution, and then noise issues. So there's a lot of data loss here. Okay. So in this project, he started with a synthetic 13CO 2-to-1 data cube, and this is a simulation I performed with Orion. So this integrated 13CO map was actually made with Mali, another completely different radiative transfer code. But nonetheless, it does something similar to RADMC 3D. You have a lot of structure, kind of filamentary stuff. And then you can observe it with the early science configuration. So this is an image. If you put the simulation 4 kiloparsecs away, so this is supposed to be an unresolved massive star-forming region, how well can you actually recover substructure within those regions? And it turns out you can sort of, but not really recover structure. This is 1 hour, early science, 16 antennas, and no noise. So here's 4 hours. And actually, I don't see very much difference at all between 1 hour and 4 hours. Structure is pretty much the same. And then you can go ahead and add noise, and you see the situation gets a lot worse. So if you have some kind of limits for the water vapor, the atmospheric variability, then it makes the situation less good. But you still see that there's some structure. So if you were looking at a massive star-forming region 4 kiloparsecs away before ALMA, you would see a blob. After ALMA, you actually see that this is not a blob, but there is actually some inherent structure that's happening there. So the second part of the project was to actually quantify this structure. And he did this using dendrograms, which I'm going to talk about tomorrow. The takeaway point is that the structure before the observation looks drastically different than the structure after the observation. So you can really see the spatial filtering here. You can see the convolution with the beam here. So there is a lot of data loss. All right. So as far as you guys are concerned, there are really only 2 main tools in CASA that you would use to do these types of post-processing. The first one is called SimObserve, helpfully named after observing simulations. So given some brightness map or cube of your data, it generates these UV visibilities as would be observed by a specific configuration of antennas. In this configuration, they have a bunch of different files, and you would choose it and say, OK, I want to look at the full science configuration, or I want to look at half the antennas, or you can also look at Karma, VLT, and a couple of other different options. So in this process, you can also add in synthetic, realistic atmospheric conditions and noise. Okay, and again, the models for these conditions and noise are kind of pre-computed, so you don't have to worry about the details of understanding the atmospheric variability, which is extremely helpful. So the second tool that you would use is SimAnalyze. And SimAnalyze is almost what the observers are using. So they get their data, and it's in this form following this step. And then they need to actually remove artifacts, clean it, and try and get back to the real sky image as much as possible. So the SimAnalyze is the tool that does the cleaning and also helpfully produces some different maps. So it does difference maps, it computes the fidelity, it tries to quantify the noise. So in this case, some of this analysis is actually done for you in a very nice, easy way. All right. So now we have the final iteration of the people stare at code. And then tomorrow we will not do that anymore. OK, so the scripts for setting up CASA are really as easy as they could possibly be. So you have the two tools. Basically what this is you set up the input parameters here. This default SimObserve says, I am setting the parameters for SimObserve. You set the parameters and then you call SimObserve. So it is really easy. Okay, but what are these actual parameters? So the parameters can be a little annoying if you're a theorist. So the first thing is, okay, name the project. So give it an output file named sim. Then you need the sky model. So the sky model is basically your data. So that might be a 2D integrated column density map. It might be a 3D data cube, position, velocity, one of those things. Now the annoying part starts here, in bright. So you need to put your data in observational units, which means Janskis per pixel. So, the best thing to do is actually take the actual data that you have and convert using some kind of radio transfer or approximations for each pixel into Janskis per pixel. But you can cheat. You can say, okay, I have some real observation I'm comparing with. It has a peak brightness of 0.06 millijanskis per pixel, so I'm just going to set in bright to this. In bright is just the maximum peak brightness. So in that case, CASA will just renormalize your data so that the peak brightness in your cube is the same as in bright. So I personally recommend that you actually go ahead and do the conversion self-consistently and not just pick a value, because it's an interesting exercise to see how well your data actually would agree with the intrinsic brightness of whatever you're observing. Then you need to pick a direction. If you're comparing with a specific region, that's easy. Then the pointing direction is simply that region on the sky. So given the distance to your region, then you need to set incel, which basically says this is the resolution of a pixel when this object is placed at that particular distance. Then you need to know the frequency center, which you need to pick some sort of molecular transition, some sort of wavelength, and that's simply whatever that is. Here is 230 gigahertz. Then you need to pick the width at which the frequency over which you're observing this particular object. So some of these things can be taken directly from whatever observation you're comparing to. Then you have these pointings. The main thing here is that you choose the integration time. So there's two different time scales here. There's the total time of the observation, okay? So that would be the total time you're physically looking at this object with CASA, or that was used to observe. But then there's a time within that, the pointing time. So how many pointings do you take? How often do you take these pointings over that total time? So this is really the pointing time, or which gives the distance between those dots in the visibility function. So here, the default is 10 seconds. For some reason, this is set to 600. So you can play around with this, and it makes some degree of difference for how often you do the pointings. Then you don't need to reset the direction and map size. You've already set it up here. Set the map type. Is this a square observation or a hexagonal, something like that. Then your antenna list. So that's one of the most important things to set. It's really the point of this whole exercise. So whatever interferometer you're trying to model, for example, this one is ALMA cycle 0, the compact configuration. So you can play around with how good your resolution is for these different files. And again, this is really nice. You don't have to make them yourself. They already exist in a library for you. Then you have the date of the observation, the angle of observation, the total time. So of course, if you pick longer times, you're going to have a much better image. But this is particularly helpful if you're trying to make predictions for something and you want to tell an observer how long they should request time to actually observe a particular object. So if you have a particular line that you're predicting, like the presence of water or something within a disk, then this would be helpful to tell them how much time they need to get the sensitivity to observe a particular line or a particular feature. Let's see. And then if you wanted to compare a single dish with the multiple antennas, you could change these parameters here. So for example, you probably don't care about what would happen if you just observed with a single dish, but you could set that and look at that for comparison. Finally, you would set thermal noise. This graphics thing is whether you want to display, just to have it pop up, or whether you want to have it saved in a file. And then basically after you set all these, you can call SimObserve. Now, most of these already have default values. So really, the most important thing is the time, the configuration file, and the resolution and brightness at the beginning. OK. So once you've done that, then you have your artificial synthetic image. But then you need to do the extra step where you clean it and recover the initial data. So this is done by SimAnalyze. SimAnalyze, again, you're basically resetting the same parameters that you set before. And this default just says that you're now using a different tool. So again, you have the direction, the image size in pixels, whether you want to, and then the analysis. We'll do some basic analysis to get differences, to get fidelities for the different images. And then this is basically, there's a bunch of these different things you can have it output. And we'll just tell you all of these different stages, what the beam looks like, what the visibilities look like, what the cleaned and uncleaned image look like. So you can play around with what those things look like in total. OK. So this is really easy. Once you've set up the script, you can call CASA Pi. It also has a GUI interface, which I usually don't use. Usually I just use the command line. So if you want to learn more about these parameters, you can do help SimAnalyze, and it will helpfully tell you every single parameter and what they mean. And then if you put all these things into a script called myscript.py, you can run it within CASA just doing exec file. OK. So then just for reference, if you want to set one of these up, the antenna configuration files can be found here. So I've installed this in my user directory, my home directory. But I mean, it's a really simple installation, so you could easily install it on your laptop and use it. Because this is based on Python, you can actually do parallel runs with this. I haven't done it, but it might make things easier. Some of these, particularly the long integration times with the cleaning, can take quite a number of hours in serial, so that can be a little bit annoying. OK. So moving on to the suggested project. So pretty straightforward. So take one of the simulations you have done over the course of this workshop or something that you have, and I suggest that you compute a kind of column density map. So some kind of integrated continuum emission map. So it's easier if it's a 2D map. You can also do position velocity, but this is the easiest thing. So once you have the 2D map, pick some, well, ideally convert it to Janskis per pixel and feed it through CASA. But you could also just pick whatever brightness you like and see what happens. And then compare this for two different observation configurations, maybe ALMA cycle 0 and ALMA cycle 1. So inputs are your column density. And depending upon what wavelength you want to look at, you probably also need the gas temperature if you're going to infer itself consistently. And then your outputs are simply the convolved image, see what CASA gives you. The extra credit is, OK, well, you can compute the integrated dust map very simply just by integrating with analytic formulas. You can also use Hyperion to do it. So if you want to do this in a really fancy way, you get Hyperion to actually do the emission self-consistently for you in a particular wavelength. And then you can use that map to feed to CASA. So if you're going to do it the easy way without Hyperion, then you basically have to follow this step where you compute the flux at a given frequency. So in the long wavelength regime, this is actually pretty simple. Okay? It just depends upon the total column density, the temperature of the dust, and the opacity at that wavelength. Okay? So I put up just a number of formulas that will help you do that. It's not too difficult, but just a little bit annoying. OK. Do you have any questions about the project? Yeah, I'm guessing you guys are pretty overwhelmed by this point with all the different codes and projects. But these will be up online, and if sometime later at the end of a paper you're writing you think, oh, maybe I can make an ALMA, prediction, then maybe you can come back to this and then give it a try. So this is a reference for you guys. Okay, final references. There's actually a very helpful online course on radio astronomy, which I would encourage you to look at if you don't have a background in interferometry, which I do not. And you also have the CASA user manual. And finally, you can email NRAO if you have problems running it or any general questions. All right, so that's it. I'll take any questions you have.